using the rational root theorem to solve polynomial functions and find all the zeros, even the irrational and complex zeros. So we have this. Let's see if I can make it bigger. If a polynomial function is in this form, you're like, whoa, that's a lot of variables. But basically all this stuff is coefficients or exponents except for x. With degree greater than 1, so it's at least linear, or quadratic, or cubic, or quartic, or something higher. With integer coefficients, and the constant isn't 0. If the constant is 0, you got to factor out x and then try this approach. Then every rational 0, where we have p's over q's, you guys might remember the p's over q's. Okay? P's and q's have no common factors other than plus or minus 1. P is an integer of the constant term, and q is an integer of a sub n. So what we're going to write down for this is we have our polynomial function. P is going to be the lead term coefficient, or the coefficient, P is going to be the constant from our function when it's in standard form, and q is going to be the lead coefficient. The rational root theorem, which we're going to talk about and use on the other side, allows us to generate a list of plus or minus factors of p divided by plus or minus factors of q. And that list would give us all of the possible rational zeros. We could test those in our calculator to see which ones actually are zeros, and then divide them away to see what's left and solve for the remaining zeros, the irrational and the complex zeros from there. And you did that in Algebra 2, but it's been a while. So now, wait, where'd it go? The rational root theorem does not give any information about irrational or imaginary roots. Right? This is only going to give you rational zeros, a list of possible rational zeros. So any that are complex, involving I, or that are irrational, probably not going to involve pi for what we're working with, you're not going to be able to find. You like that one, you'll like the other ones better. All right. So we have this, which is, now this is the 3 things that you have on your paper that you can fill out. I'm not going to be able to project and fill them out at the same time. If the 0 is rational, if the 0 is irrational, if the 0 is imaginary. Okay? So if the 0 is rational, the 0 will appear on our list. When we list out all the possibilities using the rational root theorem, it'll be on that list. And we can test this in our graphing calculator to see if it actually gives us a 0. We'll see on the graph that it will cross the x-axis or be tangent to, that's where it says bounce, cross or be tangent to the x-axis at that point. So it'll cross or bounce at the x-axis. And we can actually get that 0 right off the graphing calculator as a fraction, not an ongoing decimal. If it's an ongoing decimal, then it may not be rational. We'd have to see if we could convert it to a fraction or not. So honestly, in Algebra 2, all you did was generate your list, find one that was a 0, divide it out, get your next polynomial. We're going to be repeating that process here. Irrational. If the 0 is irrational, well, there's your next thing, Ben. Right there. The 0 will not appear in the list because it doesn't have square roots on that list. We can't generate them using coefficients. We will still see it cross the x-axis, but we can't get it from the calculator, not as an exact value, only as an approximation on a decimal approximation. Also, the irrational numbers come in a pair. And you know this because when you solve using the quadratic formula, you get the plus or minus square root, right? Same thing with the complex answers. They're going to come in pairs. Can't get them from the calculator, can't get them from our list. We have to use quadratic formula to get them. Now, those both cross the x-axis. The imaginary don't. Okay, if you remember from, and I'm going to go back to that in a second, right? Remember when we had imaginary solutions for quadratics back in Algebra 1? It was above or below the x-axis. They never actually intersected. Well, that's what you're going to have with these polynomial functions. Now, instead of having a function, a quadratic, you're going to have a polynomial, and maybe it crosses in some spot, but in others, you're going to have maximums and minimums. You're going to have turning points that don't actually ever intersect, so you lose a couple zeros there. Okay, wrong screen. So, for our imaginary, here you go. There you go, Ben. Right there. You've got a 0 will not appear on the list because it's imaginary. The graph will not cross the x-axis. You'll see some of those turning points where it's above or below the x-axis, your local minimums or local maximums. And then we'll have imaginary numbers that come in a pair. They also come in a pair just like our irrational, because the imaginary are also often irrational, not always. All right. Under the calculator, in our calculator, there is a trace button. Hold on, let me go back to this screen. Second trace. And we can actually use that to see if we can find the roots. Okay? And we can also use the discriminant. If you've gotten it down to a quadratic, or even a quartic, as long as it has that thing where the middle term is half the exponent of this one, we can even check that to see if it's going to be factorable. Same way, if it is positive and a perfect square, the discriminant, then it's going to be factorable, and we're going to have rational zeros from that. If it is positive but not a perfect square, we're going to have our irrationals, and if it's negative, we're going to have our imaginary or complex. Thank you. There's a copy over there on the desk. So, but we can actually use the graphing calculator, so we'll do that with one of our first functions. We can trace it to see if we can find the zeros. We can also do second trace to calculate the zeros, just like we did the local maximum and local minimum when we were doing extrema. So for this problem, we're supposed to list all possible zeros, then determine which are zeros and solve. So what is the value of p for this function? 4. So those are going to be factors of my numerator. Remember, I'm supposed to put p's over q's. Q is 1. So my factors of 4 are going to be plus or minus 1, plus or minus 2, plus or minus 4. And q is just 1. If I divide those by 1, I'm still going to get the same numbers. So there are 6 possible zeros. I'm going to put this in my graphing calculator. And I honestly just like using this list. I almost never look at the graph. But some of you who are visual might prefer to look at the graph. So I'm going to have x cubed minus 3x squared minus 2x plus 4. And I hit graph, and sure enough, the graph intersects the x-axis at 3 places. Now I can do second calculate, find the 0. Well, there's one of them, so I go to the left, I go to the right. That one is not a whole number, and it doesn't look like a decimal value that I could get. I could even try math convert to fraction. It won't allow me. It says syntax error because it's not going to be able to convert to a fraction. So that's one of my irrational, and they come in pairs. So one of the other ones is irrational too. So I'm going to come to this 0, go to the left, go to the right, hit enter. That one is a rational 0 at x equals 1. I'm going to go to the graph. The other one has to be irrational. I'm not even going to bother because I know they come in pairs. Now, I don't normally do it by the graph. I normally do it by the table. We have our list of possible zeros up here. I have my function plugged in. I go to table and I plug in the values of 1 and negative 1. You could even do the other ones, but usually once we find 1, we stop and then reduce the polynomial function by 1 degree. Yes, sir? 3 will not be up here because it's not a factor of 4. So we're looking for factors of 4 divided by factors of 1. So that's why I only have those numbers in my list. So right now I can see the only rational, this is the list of all possible rational, and the only one that works is 1. Even if it wasn't the only one that works, I would grab one of them, determine which are, and solve. So we have to solve for all of them. I would take that x equals 1. Let me make sure it was that because I grabbed the wrong one earlier. And we would divide it out to reduce this polynomial to something smaller and then try the approach again, or factor, or use the quadratic formula if we could. Dividing out 1, the coefficients on this are 1, -3, -2, and +4. So one of my zeros is x equals 1. That's the rational one. I'm left with a quadratic x squared minus 2x minus 4, which is not factorable. Factors of -4 will not add to -2. So I need to use the quadratic formula to solve this. Opposite of b over 2a plus or minus. I'm going to do the discriminant separately. That's also going to tell me whether they'll be irrational, which the graph already told us they were irrational, not that they were real, but irrational. So I got b squared minus 4 times a times c, which is 20. So that's the square root of 20, which I could break down. I did b squared minus 4ac and did the discriminant of this right here. Did you get a different answer for your discriminant? Or no? Oh, I thought you asked. So this is 2 square roots of 5, and I'm dividing by 2. So I'm left with x equals 1 plus the square root of 5, and x equals 1 minus the square root of 5. You could list those together as plus or minus. But that's all 3 roots, my real root and my 2 irrational. I'm going to pause it and go over questions. So the reason that I started using the quadratic formula is because it was a quadratic that was not factorable. Once I get it down to the quadratic, I'm either going to factor it or use the quadratic formula to get the remaining 2 zeros. On this one, this is a quartic equation. It is missing a term. There is no x cubed. I don't have to put that in my graphing calculator to look at the graph or to test for the zeros, but I will if I'm going to divide it out later, so I want to make a note of that. So this one is x to the 4th. That's worse. This one is x to the 4th minus 12x squared minus 15x minus 4. So I go to my graphing calculator, and lo and behold, because my p is -4 and my q is 1, it's the same as it was on that one. So I'm going to have the same list. Factors of this divided by factors of q. Well, q is 1, so if I divide it, I'm just going to get the factors of p. Plus or minus 1, plus or minus 2, plus or minus 4. By the way, it did tell me to list all possible rational zeros, so that is part of my answer right there. That's the list of possible rational zeros. So I'm going to put those into my calculator in the xy table, and once I find one that's a solution, I don't have to keep going. I could, but I don't have to. I know -1 is a solution, so one of my answers will be x equals -1. 4 is also going to be a solution. So I'll just make a note of that over here, that 4 is also a solution, but I'm not doing anything with it right now. X equals 4 is also a solution. None of the other ones were. So if 2 of my zeros are rational, then the other 2 are either irrational or imaginary. So I'm going to hit graph and see how many x-intercepts there are. There appear to be 1, 2, 3, 4 x-intercepts, so I'm expecting the other 2 to be irrational, not imaginary. But the same process applies. I know one of them is x equals -1. That's the first one I found. So I'm going to divide that out from this. So I have 1x to the 4th, 0x cubed, -12x squared, -15x, and -4 for my constant. Bring down my 1. I feel like I did this wrong again. Okay. It's 11, -4, that's +4. Got it. Remainder is 0. This leaves me with constant x, x squared, x cubed. So my new equation is x cubed minus x squared minus 11x minus 4. I would try to factor, because I could try to do factor by grouping, but the 11 and 4 won't have anything, so I can't factor by grouping. Since I can't factor this, and it's not a quadratic or something where there's a middle term that's half of the first term, I can't do quadratic formula. So I'm going to have to repeat the rational root theorem. But we're in luck. We don't have to really generate a new list for this one, because our coefficients, our p is once again -4, and our q is once again 1, so it's the same list. Off of that list, we also determined that x equaled 4 was a solution. So I'm going to divide that one out now. X equals 4. Put it in the box. And write down my coefficients again. 1, -1, -11, -4. 1, 4, 0. This leaves me with a quadratic of x squared plus 3x plus 1. And now that it's a quadratic, I'll try to factor it, but I already know it's not going to be factorable because only 2 of my zeros were rational, the x equals -1 and the x equals 4. This isn't factorable. We're going to have to use the quadratic formula. The discriminant b squared, which is 9, minus 4 times a times c is 5. So I have the opposite of b plus or minus the square root of the discriminant, which in this case was 5, each over 2. I have my rational and irrational parts separated. So those are my two answers. My two irrational answers are -3/2 plus the square root of 5 over 2 and -3/2 minus the square root of 5 over 2. I could put that in my calculator for a decimal approximation, and I could look again at those zeros on the graph, and sure enough, they would turn out to be that, not those two numbers. But this came in a pair. There's 2 of them. So there's my 1, 2, 3, 4 zeros for that one. Any questions on that? All right. We have the next one, which again, they ask for a list of all. These one, the leading coefficient isn't 1. So we're going to have fractions, not just the factors of p. We'll have to divide them by all of the factors of q. List all the possible rational zeros. I'm going to do that in pink. My p is -5, since this is in standard form. My q is 4. So my factors of p are 1 and 5. My factors of q are 1, 2, and 4. And I have to make a list of my p's divided by my q's. Well, if I divide these by 1, that's going to give me plus or minus 1 and plus or minus 5. 1 divided by 1, 5 divided by 1. When I divide by 2, I'm going to have, these factors were 1 and 5, plus or minus 1/2, plus or minus 5/2. When I divide by 3, or not 3, sorry, when I divide by 4, I'm going to have plus or minus 1/4, and then 5 over 4 plus or minus 5/4. So I took the two factors of p and put them over each factor of q. It gave me a list of 6 that I've listed, but since there's plus or minus, there's actually 12 possible rational zeros that were generated from those from that constant and that coefficient. I'm going to use my graphing calculator to find just one of them and divide it out. How many times for this problem do you think I'll have to do the rational root theorem, given that it's a cubic equation? Just once, because after I divide out a factor, I'm going to get a quadratic that I can either factor or use the quadratic formula for. So I have 4x, let's go to y equals 4x cubed minus 20x squared plus x minus 5. I go to my table. I already have 1 and -1 entered. They aren't zeros. 5 is a 0. I don't even need to find the other ones right now. I can if I want to, but I don't have to. There probably aren't going to be any anyhow for this one, but there might be. So 5 is one of the zeros. X equals 5 is the first one I find. That's one of my zeros. I'm going to divide that out synthetically to break it down to a quadratic. So 4, negative 20, 1, negative 5. I'm left with the following quadratic equation. 4x squared plus 1. Two of my zeros, one of my zeros is right there, it's rational. Two of my zeros are here, they're irrational because I can't factor this. But I could set it equal to 0. I could either do the quadratic formula if you want, but I'm actually just going to subtract 1, since it's just an x squared, and divide by 4. X squared is negative 1/4. When I take the square root, it's plus or minus the square root of negative 1 over 4, so I'm separating that. It's going to give me plus or minus I over 2, or plus or minus 1/2 I. So my other answers are I over 2 and negative I over 2. So I have one real that is rational and two complex answers. In fact, if I look at the graph, I should only see one x-intercept and then one of either a local maximum or local minimum below. I need to change my window so you can see it a little bit better. I'll do negative 100 and positive 1. I don't need to do positive 100. Oh well. You can see this one touches, or actually this one intersects. This maximum and this minimum both fall below the x-axis. There's only one rational zero. The other two have to be complex. All right, I'm going to skip the middle one only because it has a lead coefficient of 1, and I want to focus right now on ones that don't have. No, I want to do the middle one. We're going to do the middle one, and then we won't finish this one. We'll just generate our list for that one to save time. So for our middle problem, I'm going to do this. Guess why I decided to do this one and not the next one? Anyone have an idea? What degree is it? 4. So I'm going to have 4 zeros. So I'm going to have to possibly use the rational root theorem at least once, maybe twice, to get it down to a quadratic, unless I can factor. I can't factor this, though, so I have all these terms. The p is 36, q is 1. It's nice when q is 1 because I don't have to worry about fractions. So all the possible factors would be plus or minus 1 to plus or minus 36. That's going to include 2 and 18, 3 and 12, 4 and 9, and then 6 and 6, so plus or minus 6. So those are all, I kind of listed them in a weird order, but wanted to make it fit. So 1 and 36, 2 and 18, 3 and 9, 4 and, 3 and 12, 4 and 9, and 6. All of those multiply or are factors of 36. So I have all of those. I only need to find one to start dividing it out. So I go to my calculator, I put in x to the 4th minus 6x cubed plus 13x squared minus 24x plus 36. And 1 isn't a 0, neither is negative 1. 2 isn't a 0, neither is negative 2. 3 is a 0. So since x equals 3 is one of my rational zeros, there could be more, there probably are. I'm going to divide that out to start. So I have 1, negative 6, 13, negative 24, and positive 36. By the way, if you want to know more about your zeros, whether there will be multiplicity or how many are irrational or irrational or not real, you could look at the graph. But I'm still going to follow this process to solve. Bring down the 1, multiply by 3. 12, negative 36. This leaves me with a cubic equation, x cubed minus 3x squared plus 4x minus 12. Any questions so far? At this point, I could repeat the rational root theorem with the numbers 12. So 12 over 1, 1 over 1, 2, 3, 4, 6, and their opposites, and find another rational 0 and divide it away. But there is a quicker way to do this. Does anybody see it? I can factor by grouping. Cut that four-legged animal in half. That's how I teach that. We're hunting animals. This one's got 4 terms. We cut it in half. The greatest common factor of these 2 terms is x squared. The greatest common factor of these 2 terms is positive 4. When I factor out the x squared, I'm left with x minus 3. When I factor out the 4, I'm left with x minus 3. If you can factor it, great. It's going to save you time. If not, then you got to do rational root theorem again until you get it down to a quadratic. So now I have 2 terms. The greatest common factor of those 2 terms is x minus 3. So I have x minus 3 times what's left is x squared plus 4. And I have to solve. This was a quartic equation. We already had one rational 0. This is going to give us another, hey, wait a second. They're the same thing. So what does that have? Multiplicity. If I look at the graph, I should see it bouncing at x equals 3, being tangent to the x-axis. And then this one I'm going to set equal to 0. So I have x squared plus 4 equals 0. Minus 4, this is going to be too complex, I think. X squared equals negative 4. Take the square root of negative 4. I'm going to get plus or minus 2i. So 2 of them were imaginary or complex. And then one of them was a real 0 with multiplicity of 2, accounting for all 4s. 1, 2, 3, 4 zeros. Take a second to list just the possible. I don't want us to solve this one because we need to do some other problems today too. I want you just to list all of the possible for this. The possible rational zeros. Your p is 5, your q is 2. See what you can generate with that for your list. Nobody? What numbers are going to be on top for every fraction I write? 5 and 1. So when my factors of 2 are 2 and 1, those are going to be in my denominator. Factors of 5 are 5 and 1. Those are going to be in my numerator. So I have plus or minus 1, plus or minus 5. That's putting those over the 1. And now I'm going to put them over the 2, plus or minus 1/2, plus or minus 5/2. So I've written 4 down, but with the plus or minus, there's actually 8 possible. And we could find those by putting them in our calculator, and then if we need to divide them out, we could. When I divide one of them out, what type of equation would I get if I divide one of those rational zeros away? I'll get a quadratic, yes. And I can either factor or use quadratic formula to get the remaining 2. All right, our last couple problems. We have this one. It says solve the polynomial equation. What's different about this compared to this? Well, this one I had it was a function. F of x equals this, and we're supposed to find the zeros. We're finding the zeros, so we set it equal to 0 is what we were doing. This one, it's not just a function. I mean, we could write it as a function, but we have an equation there. What do I need to do? Subtract 12 from both sides to get it equal to 0. But we're still determining when this function would have a height of 12. That's what this is really saying. When does this function have a height of 12? Okay, we can find that, but we have to get it equal to 0 to solve. So we're going to subtract 12 and set it equal to 0. This makes our value of p 12. So I've got, and the value of q is 1, which is convenient. So I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, 6, and 12 as all of my possible. Now it didn't ask us to list them, so if you didn't generate the full list on this, that would be okay. But on problems where it says list all possible, you have to generate the complete list. For this one, I'm going to plug in x to the fourth, plus 2x cubed minus 7x squared minus 20x minus 12. I'm just going to try to find one of them. Hey, the first one that popped up was -1. So we got x equals -1 as one of my rational zeros. I'm going to divide that away. Make sure there are no missing terms. And see what equation I'm left with. I'm left with x cubed plus x squared minus 8x minus 12, which does not appear to be factorable. So guess what I have to do? Do it again. Rational root theorem. Good news, I don't have to regenerate my list because, lucky for us, the p is the same as it was before and the q is the same as it was before, so I'm not going to find any new ones here. These are all the same list. If it was a smaller number, I might generate it because then I have to test less of them. So I'm going to go back to this, and it turns out that -2 was also a 0. So I will factor out the -2. So I'm going to have -2, and that's going to be 1, 1, -8, -12. So I've got x equals -2. I've got 2 of my zeros already. I'm going to write those down over there. This is x squared minus x minus 6, which is factorable, so all of my zeros are rational. This will be x minus 6 by x plus, no, x minus 3 by x plus 2, multiplying it to -6, adding the -1. That gives me x equals 3 and x equals -2 as my remaining two zeros. So I have -1, -2 apparently has multiplicity because I found it once already. So I have 3 of them, but this one has multiplicity. Questions on that? All right, our application problem. This says the water level in a bucket sitting on a patio can be modeled by this cubic equation where f of x is the height of water in millimeters, and x is the time in days. On what day will the water reach a height of 10 millimeters? So what am I going to do with this equation? Should I plug 10 in or set it equal to 10? Equal to 10. I could do rational root theorem if I want. It's not factorable. What I'm going to do is subtract the 10 from both sides, get it equal to 0, and see if I can find it on my calculator to save us a little bit of time. Because it's not telling us to solve, it's just gave us a story problem. So I'm okay with us using the calculator to try and find that 0. So x to the third plus x squared minus 7x plus 2. And I'm going to go to second table, actually not table, I'm going to go to the graph. Might want to change the zoom, but whatever, zoom standard. And I'm going to find my zeros. Since we're talking about on what day, do you think I want this one back here? No, because we're not going to go backwards in time. So I'm going to go to second trace for calculating the 0. I could guess I could do this one right here. That's 0.3, which isn't even a full day. So probably not, maybe. And then I'm going to go to second trace, find the 0. And I get 2. That 1 times e to the -12th is really 0, so I do get 2. So x equals 0.3 or x equals 2. Since we're looking for whole number days, our answer is 2 days. And that's what we would have gotten if we took out our rational zeros too. One of the rational zeros would be 2. The other 2 are going to be irrational, and they're not the ones we're interested in. Try this for the next problem. You can use your calculator to help you solve the problem once you have it set up. Or you could, because it's a quadratic, use the quadratic formula.